Hey everyone, my name's Praveen and I'll be guiding y'all through the mini lecture for discussion one this week. So basically what the mini lecture is going to look like is kind of a content review that can be helpful for the practice problems we're going to do in discussion as well as the homework. Um, your actual TA in your in-person discussion will go over introductions, deadlines, policies, logistics, and potentially an icebreaker, things like that. Um, but I'll leave that to them and kind of just talk about what discussion in general will look like. So this right now is the concept review, basically what you would watch before section. Um, the mini lecture, a lot of me talking, kind of going over relevant content in case you want to reference it. And then in section is where you'll do most of the learning. So you'll be doing a worksheet, practice problems, asking the TA questions, and getting those answered. So today we're going to cover an intro to linear algebra that's relevant for this course, calculus, as well as a little bit of probability and sampling. Okay, so starting off, linear algebra, some of y'all are taking it now, in which case it's a preview. And for others who have taken it already, this is kind of a review of the concepts that are going to be foundational for our applications of linear algebra in this class. This is super helpful for homework 1B and, of course, the rest of the class. So we'll start off with vectors and matrices. So what is a vector? Um, you can kind of just think of it as a list of numbers for our purposes. In terms of like how you could visualize a vector, it's, for example, in this vector, we have three numbers, in which case the first one would refer to the x direction, the second one refer to the y, and the third would refer to the z-axis. So those are those three. If you wanted to, we could visualize this visually. So I will reduce it to just being 2 dimensions because I don't want to draw in 3 dimensions. So if we have, an axis, you can draw a vector as well. So we could just quickly kind of label it. So if we have this vector here, vector v, with a weight of 1 in the x direction, a weight of 2 in the y direction, you would look at this graph and be like, okay, it's 1 in this direction, 2 in this direction. And so the actual vector would be over here, like so. For us, usually we just think of it as kind of a list of numbers and they're usually related somehow. So a matrix is a collection of 3 vectors in this example. And you can think about vectors and matrices in a lot more complex ways, especially with different mathematical applications. But for now, at least, we'll just think of it as a collection of vectors. What can you do to vectors? So we can scale vectors by constants. So this is one example, 3 being the scalar in this case, and you would just multiply it by every number in the vector and get 3, 6, 9. And so if you were imagining that vector that we drew on the previous page, if now I was going to draw 3 times the vector v, it would get 3 times longer. I won't measure it out, but you get the idea. So if we go back here, you can also add vectors to one another. So we have the vector we started off with. We have a scaled vector here, which would give us 2, 2, 2, and then we can add just each row. So we get 1 plus 2 is 3, 2 plus 2 is 4, 3 plus 2 is 5, and we have the resulting vector. Okay, matrix multiplication. So we can multiply 2 matrices or a matrix and just a vector, which I'll show in this example to produce a new matrix or vector. And I've kind of labeled it with a lot of colors here, but basically like how I like to imagine it is when you have a vector here and we're multiplying it by a matrix, I basically imagine as me picking up this orange box and laying it on top of the matrix, row by row. So first I'll pick this up and literally like imagine turning it and placing it here. and each number that overlaps is what we multiply. So if I were to pick this up and lay it flat this way, the 1 would overlap with the 1, so I would multiply those. The 2 would overlap with the 0, so I would multiply those. And then the 3 would overlap with the 1, so I would multiply those. And basically, the parts that overlap, you multiply, and then you add those products. So if I add this together, we get 1 plus 0 plus 3 is 4, and that's what goes here in this top box. So you could see it based on the colors. It's where the orange and the blue overlap, so to say. So you would do the same exact thing for every other row in the matrix. So we take this again, and now we overlay it with the second row of the matrix. So we get 1 times 0 is 1, 2 times 1 is 2. I mean, 1 times 0 is 0, 2 times 1 is 2, and 3 times 0 is 0. So you just get 2, 0 plus 2 plus 0. And then the last case, we would take the vector, flip it to line up with the 0, 0, 2, multiply the overlapping numbers, and because they're 2 zeros, these would become multiplied to 0, and we just left with 2 times 3, which is 6. And that gives us our resulting matrix or vector based on what problem we're doing. So this example, we have a matrix and a vector. And so we get a vector at the end. We can also do matrix with a matrix, so I'll do this example here with y'all. And the difference here is now that we have to do what I just went through with y'all at the top kind of twice, because we have 2 column vectors to work with now. So we would do this process for this column vector first. I kind of overlay it this way with the first, second, and third columns, and then do it again with the second one. Okay. And in general, whenever you do matrix multiplication, I would use this kind of trick here at the bottom to figure out what your resulting matrix will look like to make sure you do the math properly. So in order to do any type of matrix multiplication, you want to think about what the dimensions of the matrices are. So this first one is 3 by 2, and the second one is 2 by 2. Or 2 by, I changed it. Sorry, this is 2 by 2. And in order to do the multiplication at all, if you think about it the way I just described with the overlapping, you'd realize, right, that the height of this vector has to match the width of this matrix in order for them to overlap and us to be able to do the multiplication at all. So what that translates to is these 2 numbers here, right? They need to match. In order to be able to do the multiplication. And then your resulting matrix will be based on the dimensions, the other dimensions. So you can refer to this later as well, but these have to match, and then your answer, your resulting matrix, will be the dimensions that are left over. And the way we write dimensions for matrices, in case you, for a reminder, is rows times columns. So our resulting matrix will be 3 by 2. So that's 3 rows by 2 columns. So basically the same size as the first one. Okay, so now we can work through it together. If I'm going to start off with this first one right here, I would do 2 times 1 is 2, plus 6 times 1 is 6, and that gives me 8. 2 times 2 is, now moving on to the second row here. 2 times 2 is 4, plus 1 times 6 is 10, and so on and so forth. And then I would do the exact same thing for the second row and kind of go down. And because these columns are both the same, I would get the same numbers here. Yeah, to finish it off, 6 plus 6 is 12. So if you were going to practice, you could use this example. The most relevant thing here is probably this kind of trick in order to make sure that whenever you're doing your matrix multiplication or setting up matrices for multiplication or writing formulas that involve matrices and multiplication, that this follows through because it's an easy way to catch your mistakes, is to double check that are you even multiplying matrices that can be multiplied. And if not, then you can double check your work. We'll move on to linear independence. So we say a set of vectors, right? We're talking about a set of vectors. We say a set of vectors is linearly independent if there is no way of adding and scaling those vectors to produce the zero vector. So if we're looking at these three vectors, this as our set of vectors, we would say that this set of vectors is linearly dependent because we can add them, subtract them, scale them in a certain way that gives us the zero vector. So in this example, these two vectors, 1, 2, 3, and 1, 1, 1, we can add them in a certain way that gives us 3, 4, 5, and thus they are not linearly independent because we can then subtract the 3, 4, 5 and get 0, 0, 0. I normally like to think about it as, can I get one of the column vectors from the other ones? So in this set over here, I can get this one with just these two by doing some form of scaling and addition and subtraction. And so that these are not all independent. This one, I kind of like thinking of it as if this one doesn't really add new information, I could have just gotten it from the information that I already had. Yeah. So related to linear independence is column rank. The column rank of a matrix is the maximum number of columns that we can take from the matrix to still have a linearly independent set. So basically, how many of the columns are linearly independent? And we want the max, right? So in this case, these two columns are linearly independent. As soon as we add the third column, it becomes dependent, so we wouldn't count this. This would give us a rank 2 because we have two columns that are linearly independent in this matrix. A couple of other kind of vocab words or types of matrices to be familiar with. They're inverses and transposes. So for an inverse, the notation is a -1 in the exponent. And basically the point is if you have the inverse and you multiply a matrix by its inverse, then you will get the identity matrix. The identity matrix is this one here with the ones on the diagonal and zeros everywhere else. The identity matrix is a matrix that you could multiply by anything and just get the same matrix. So if I called this matrix the identity matrix times matrix A is just A, and it works both ways. It is important to note that matrix multiplication is not commutative, like we can't just switch them arbitrarily. It does work for the identity matrix though. Okay. Importantly, the inverse of a matrix only exists if it's a square matrix and it has full rank. So the inverse, that's this right here, to make that arrow clear. The inverse of a matrix only exists if it's a square matrix and it has full rank. So full rank meaning all the columns, like we just talked about, all the columns are linearly independent. We'll be doing some work later in the semester where we need to know if a matrix is invertible. And so these are some of the requirements for a matrix to be invertible. So it's good to keep in mind. The next topic, last topic is transposes. Basically a transpose of a matrix has this notation, a little t at the top, and all the rows switch to columns or all the columns become rows. So here in this example, on the side. The 1, 3, the first column becomes the first row, and second column becomes the second row, and so on and so forth. So this is just another example. For your reference, I've included a slide with more detailed properties of invertible matrices, but I won't go through them, and we'll expand on this more during the class. Okay, so that's our linear algebra review. And now we'll move on to some calculus that's relevant for the course. The main thing that we're going to talk about in today's mini lecture are partial derivatives and a gradient, as the prereqs for this class don't necessarily include multivariable calculus. This is kind of the portion of multivariable calculus that we'll be using. And I'll go through it now. So the derivative of the function with respect to one of its inputs is the partial derivative. So if we kind of compare this to a function perhaps that you work with in non-multivariate calculus, we have f of x normally is usually one variable involved. And now in this class and in general, you can have functions that have more than one variable involved. So here we have both x and y in our function. And we just need to know how to take the partial derivative. So in order to take the partial derivative, it's the same as a regular derivative, except whatever you're taking the derivative with respect to. So for example, normally when we take the derivative of this f of x, we take the derivative with respect to x. Now when we're going to take the derivative of this multivariate function, we have the option to take the derivative with respect to x or take the derivative with respect to y. So over here we're taking the derivative with respect to x. And so when you're doing that, everything other than x would be considered, or you treat it like a constant, right? So the y cubed, we just act like it's some number and then take the derivative the same way that you would or you have been doing in your calculus classes. So important thing to note quickly is the notation of a partial derivative is not the exact same as a derivative, a regular derivative. So regular derivative, we have like lowercase d. Partial derivative is lowercase delta, so it's a little rounded. So that's how you'll be able to tell if it's a partial derivative. So here we do the power rule like you have learned in your calculus classes. And just like normally you can leave the constant alone in this case, we would leave the y cubed alone and just remains there as if it were a constant. So that's partial derivatives. And then the gradient is basically the collection of partial derivatives with respect to every variable we have. So we could, for this example, if we were going to write the gradient of this, of this function that we just did on the side, we would write the partial derivative with respect to x at the top. And then the next row, or like the next element in this vector, would be the derivative with respect to y. So this is a vector. The gradient is a vector that just contains all of the partial derivatives for a function. Okay, as a reference, I've included some common derivatives that you would have learned in your calculus class. I'm not going to go over them, but just as a reference for review in case it's been a while since you've done some derivatives. Next topic we're going to cover is probability and sampling. To get data, we sample populations that we're interested in. We do studies. Also, for example, if I was interested in the UC Berkeley student population and I was doing a study on them, I would most likely not be able to get all UC Berkeley students to participate. So I would be studying a sample or a subset of those people. And whenever we sample populations, it comes with probabilities, right? The chance that someone at UC Berkeley is included in my sample um, is a probability and it's relevant. We can calculate that chance, right? The chance that any given set of individuals will be in my sample. And this calculation, these probabilities allow us to estimate the bias and chance error in the sample, which we'll talk about later in the course. For right now, though, the main thing to think about are the two iconic examples of studying samples. We have random sample with replacement and a simple random sample. So we can kind of break down what a random sample is, first of all. So when we draw like at random, that's what you think of, right? The second part here is that drawn uniformly. Uniformly just means that every person in our population where we're choosing people from or choosing objects from or whatever have the exact same chance of being chosen. So it's uniform. Those chances that I was talking about are uniform. They're even or equal across the board. So every single UC Berkeley student would have the exact same chance of getting chosen. The third part here, that's the differentiation between these two types of samples, are whether you are drawing with replacement or without replacement. So the easiest way to think about this is kind of like, say you have a bowl of marbles, right? We have this bowl of marbles. We have some marbles in it. So we have 3 red marbles and 2 blue marbles. There's kind of 2 ways we can choose our sample. So let's say I'm going to choose a sample of a total of 2 marbles. That's my sample size. That's what I'm choosing from this bowl here. If I were thinking about a random sample with replacement, then when I choose my 2 marbles, I would randomly choose my first marble. Let's say it's this red one. I choose it. I'm like, okay, this is my first marble. When I go to choose my second marble, I would actually leave this or put the red marble back. If you want to say like with replacement, I'm replacing the red marble back in the bowl before choosing my next marble. So then I would choose another marble at random. And let's say I get another red marble. So the point is that both times that I was choosing a marble, I had the same chance of getting a red marble, 3 out of 5 chance of getting a red marble. And the second time I did it was still 3 out of 5 chance to get a red marble. The second option we're looking at here is a simple random sample without replacement, meaning I don't put the first marble back after I pick it. So in this case, my chance of getting a red marble on my second draw after I already chose a red marble would now be 2 out of 4. Because there are 2 red marbles out of the 4 marbles that I have. And it's different because I'm not replacing the first red marble without replacement. So that's kind of terminology that's very common in probability, simple random sample. The main idea is that you're not replacing whatever you chose. So there are some rules here that are kind of the basis of probability. So we have the addition rule, multiplication rule, and the complement rule. So the addition rule is for when we're interested in studying, getting the probability of event A or event B happening, and A and B are mutually exclusive, i.e., A and B can't happen at the same time. So the example I like to think of is the probability of today being Monday or today being Tuesday. It can't both be Monday or Tuesday today. So that's how I know that these 2 events are mutually exclusive. Since they are mutually exclusive, I can split it up and use the addition rule. The probability of it being Monday or Tuesday is the probability of it being Monday plus the probability of it being Tuesday. The second rule we're looking at here is the multiplication rule. So there are kind of 2 cases we have to think about for the multiplication rule. The first case is if A and B are independent, and the second is if events A and B are not independent. And so the good example to think of is the bowl we just talked about. So above, if we kind of continue the two marble idea, let's say the two events that I'm considering, A and B, are getting a red and a red. That's what I'm interested in, kind of calculating what's the probability of getting a red marble and a red marble, both my first draw and second draw. Based on what our sampling method is, whether that's a random sample with replacement or a simple random sample without replacement, will affect what our probability will turn out to be. So let's do the first type over here. We'll start off with a random sample with replacement. Right, the probability of getting a red on the first draw and a red on the second draw, we can use this formula because with replacement, A and B are independent, meaning the probability of getting a red on the first draw is not affected by me getting a red on the second draw, and vice versa. Like we had written before, the probabilities were 3/5 both times because I'm putting the red marble back. And thus the probability of getting a red marble the second time is the same as the probability of getting a red marble the first time. Versus if we're doing it without replacement, then if I get a red marble the first time, it changes the probability of getting a red marble the second time. If I don't get a red marble the first time, it also changes it, so they're not independent. And in that case, we would be multiplying the probability of getting A, which is getting a red marble the first time, by the probability of B given A. So this given notation is like a straight line, meaning the probability of getting a red marble given that I got a red marble on the first draw. And that's this probability, the 2/4 that we got. So we already actually did this problem. But now you can kind of see how we would write it mathematically. Would be saying that 2/4 is a probability of B given A, or the probability of getting a red marble on my second draw, given that I got a red marble on my first draw. Okay, the last two rules here, we have the complement rule. So this is like, I will talk about this with weekdays. So A is Monday, right? Today is Monday. The probability of the complement of A is, you kind of think of the complement as the opposite. So the probability of the complement of A is the probability that it is not Monday today, right? So the word not is usually there. Or something similar. The probability that it's not Monday is 1 minus the probability that it is Monday. So let's say, 1 out of 7 weekdays it's Monday. So the probability that it's not Monday would be 6 out of 7. And then we usually use this only when it's easier for some reason. There's usually like certain examples where it's actually difficult to calculate this probability itself. So you can imagine if I was like, if I tried to calculate the probability of it not being Monday, I could have done the probability of it being Tuesday plus the probability of it being Wednesday plus the probability so on and so forth, which is a lot of addition. Versus in this case, I just had to subtract the probability of it being Monday. So it's a little bit faster, and there'll be similar examples in class. The last theorem or rule that we're going to talk about is Bayes' theorem. And this is what we use when we want to calculate the probability, a conditional probability, right? So the probability of A given that B has occurred. So this is the formula for that, and I'll let y'all practice it through the homework. So this is really a very brief overview of probability. There's so much more to probability than this. If you're interested, or required to, you may go on to take some of these other classes we have here at Cal that go into way more depth. But that'll be the last thing we're going to cover in today's mini lecture. Thanks for coming, and I hope you have an awesome first discussion.